In this question, it is said that a cylindrical pipe of radius r is rolling towards a frog sitting on the horizontal ground. Center of the pipe is moving with a constant velocity v. To save itself, the frog jumps off and passes over the pipe, touching it only at the top. Denoting air time of the frog by t, horizontal range of the jump by r, and acceleration due to gravity by g, which of the following conclusion can you make? Alright, so let me draw the picture. So this is the pipe of radius r. It is moving with a constant velocity v. Frog is here. So if the frog will keep on sitting here, this pipe will run over it. To save itself, it jumps off. So this frog is also moving and this pipe is also moving. So it just touches at the top. The horizontal range is r, and uy is the initial velocity, is vertical component, ux the horizontal component of the initial velocity. So we can find the time of flight. From here to here, the time of flight is, total time of motion is t, capital T. So from here to here, time of motion would be t by 2, and at this position the velocity is the horizontal, and we know that for the horizontal projectile motion, time of flight is a square root of 2h by g, and this h is 2r. So I can write this, from here to here the time of motion is t by 2, and that t by 2 is square root of 2h, h is 2r by g. So simplify this, we will get the t is equal to 4 square root of r by g, and that would be this equation. And now let's see this whole picture in the frame of the pipe, and obviously r would be ux into t. So in the frame of pipe, as we can say from the cylinder's frame, so with respect to cylinder is here, with respect to cylinder, the velocity of this frog would be horizontal component would be ux plus v, and the vertical component would same. So as frog moves like this, it touches only at the top. So if we see the radius of curvature of this parabolic path over here, the radius of curvature should be greater than the radius of the pipe. If the radius of curvature is less, it cannot cross this pipe. So at this point, the radius of curvature of the frog's path would be greater than the radius of the pipe. So here at the highest point, the horizontal component is ux plus v, and the radius of curvature is say rc, and the acceleration is the downward direction g. So we know that the radius of curvature of a path is velocity square divided by component of acceleration perpendicular to velocity. So rc at the top should be greater than or equal to the small r, that is the radius of the pipe. So rc is vx plus v whole square by acceleration g, and that should be greater than or equal to r. So just simplify this, and we'll get, simplifying this thing, we'll get ux should be greater than a square root of rg minus v, and ux is in capital R, so ux is r by t. So r by t should be greater than or equal to square root of small rg minus v. So r should be greater than capital T square root of rg minus v, and put the value of t from here. So we will get finally this r should be greater than 4 square root of small r by g into square root of rg minus v. So we got the expression connecting the range and radius and the velocity of the cylinder, and that is option D.